Welcome to Summarize Science, where we break down the latest breakthroughs in artificial intelligence. Today, we are looking at a fascinating paper that asks why our best image-making AIs are often bad at simple labeling tasks. Diffusion models are masters at generating beautiful art, but they struggle with semantic segmentation, which is the act of labeling every single pixel in a photo. The researchers behind this paper noticed a fundamental mismatch between the way these models flow and the way we need them to make discrete choices. In this visualization, the researchers show two major problems: gradient vanishing and trajectory traversing. Essentially, as the AI gets closer to the correct label, its internal guidance signal gets weaker and weaker, causing it to stall out. Even worse, because the model doesn't know it should stay away from wrong answers, its path can drift into a different category entirely. This leads to slow training times and confusing, blurry results where the AI can't decide if a pixel is a tree or a building. To solve this, the team proposed a new framework they call FlowSeg. Most previous attempts either used diffusion models as simple feature extractors or tried to treat masks like low-quality photos. FlowSeg is different because it performs pixel-level training from start to finish without needing extra auxiliary modules. It rectifies the standard way these models learn by reshaping the underlying mathematical field that guides the AI's predictions. The researchers performed a deep dive into the optimization dynamics to figure out why standard models fail. They discovered that the common mathematical objective only cares about pulling the AI toward the right answer. In a bounded space where many categories are packed together, this pulling force is often too small to be effective. Without a pushing force to keep it away from neighbors, the AI gets lost in a sea of similar-looking labels. The solution is a clever strategy called vector field reshaping. The team introduced a new correction term that acts like a magnetic force field around each category. They also used a quasi-random encoding scheme inspired by Kronecker sequences to map out these categories in 3D space. This ensures that all the different labels are spread out evenly, giving the AI a stable map to follow. This new effective target includes a reconstructive pull toward the right answer and a discriminative push away from the wrong ones. Think of it like a smart GPS that doesn't just tell you where your house is, but also warns you to stay away from the neighbor's lawn. By doing this, the AI maintains a strong learning signal even when it is very close to the final answer. This prevents the fading problem and ensures that the boundaries between different objects remain sharp and clear. To make the results even sharper, the researchers used something called pixel neural field decoding. Instead of compressing the image into a tiny, blurry representation, they treat each patch of the image as a continuous field. This allows the AI to capture fine-grained details that traditional models often smooth over. The backbone of the system dynamically predicts the weights for a small internal network, making the whole process incredibly flexible. When put to the test on difficult datasets like AD20K and CocoStuff, the results were impressive. FlowSeg significantly outperformed previous generative models and even beat some specialized discriminative experts. In these images, you can see how FlowSeg handles complex scenes, accurately separating buses from buildings and trees from sky. It achieves these high-quality results while being much more efficient than its predecessors. The researchers also compared their deterministic flow approach to standard stochastic methods. As you can see in these comparisons, older models often produce noisy or inconsistent results based on a random seed. FlowSeg, however, remains consistent and stable, which is vital for real-world tasks like medical imaging or autonomous driving. They also proved that their specific push and pull operators were far more effective than simpler mathematical alternatives. In summary, the researchers identified that the main hurdle for generative segmentation wasn't a lack of model power, but a flaw in how they were being taught. By reshaping the learning field to include repulsion and using high-precision pixel fields, they've created a much more capable AI. This work could lead to a future where one single AI model can both generate incredible imagery and understand it with the precision of a specialist. Thank you for watching Summarize Science. Be sure to like and subscribe for more deep dives into the future of tech.